Yeah, so hi everybody, welcome to the workshop. This is tidy text classification. I'm going to start just by introducing myself. My name is Andrew, I've been at Ascent for around 2 years now. My main background is in maths, and I did this sort of project not too long ago at a workshop that we presented for Earl back in September. Daniel, if you want to introduce yourself as well.
Yes, so yeah, I'm Daniel, data scientist with Ascent for also close to 2 years. I've delivered a variety of projects, including training, including delivering workshops, such as the one you'll see now. And also, it's a workshop based on one we delivered before, but it's not a repeat.
Absolutely not. Cool, so just to start, I'm just going to give the agenda. So we're going to start just by talking about why we chose that this would be maybe a good idea for a workshop, what the motivation behind it was. The vision, so really just what are we actually going to try and achieve in this workshop, what is it we tried to do in the project and how did we try to do it, and then we're actually going to dive straight into our studio and start actually doing the coding. So please feel free to code along if you feel like you want to. If you don't want to, that's absolutely fine. There will be a recording at the end, but yeah, you might enjoy it if you do want to code along. We are, of course, also going to be having exercises throughout. So I think there's 3 exercises, 2 main ones, and just sort of more of a discussion one at the end. And of course, I mean, it's not a particularly big room, so feel free just to ask questions whenever you like to. We do also have some prerequisites as well. I've had this up on screen before. Hopefully everybody's seen this as well. There was an email that went out on Tuesday just to clone that repository and then also run one of the scripts that's within that repository. That's the depends.r script. Again, if you don't want to code along, then don't worry too much about that. Just watch on screen. Okay, I'm just going to hand over to Daniel. Just start talking about sort of what made us want to do this as a project.
I will leave this microphone here and can you?
Yeah.
Can you hear me without the microphone? Is it all right? Okay, then maybe we don't need that one.
Yeah, I think we're fine.
So the idea is, well, first of all, the inspiration came. We did a workshop at Earl 2021. It was web scraping and text mining in R, and we used lyrics because just as a, the kind of data that we use for lyrics, music, everyone or most people can relate to, and it's an interesting type of data set, has its own set of difficulties. But the idea was to show sort of an end-to-end workflow of scraping your own data and then doing a text analysis on it in R. And if you like that sort of stuff, this kind of workshop, Earl 2022, is happening in September this year, and it's going to be in real life once again. The abstract submission is still open until the end of March, so if you want to do a presentation. Otherwise, let's go to a description of basically the broad context of how we essentially the whole workflow. So we use the Spotify API, which has, if anybody has never, any of you has never used it, it's really good. It gives you a lot of data, very easily accessible, and we're going to be querying it through a package called Spotify R. Gets us a lot of data on. So basically, we are scraping a bunch of playlists on different music genres, and it comes with a lot of artist data, genre data, a bunch of other stuff that we're not going to use today, like audio features. Spotify does some audio analysis on, say, how happy or how sad a song sounds. So we get a bunch of tracks with their artist names, and then we scrape their lyrics from lyrics websites such as Genius using Harvest, and then we obtain our data set. So just to be clear, today we're going to start from the data set and do what comes after, which is doing the text analysis. So we're going to be trying to do some supervised machine learning, so classification. So we're going to show you using the packages that we'll talk about in a second, pre-processing the data, creating numeric features, fitting models, and doing some model tuning. And the idea is, can we predict musical genre from lyrics, which sounds very ambitious. So there's imagine about 20 asterisks at the end of this idea, which is we're going to be using a very small subset of genres, and we're going to see if we can train a classifier to, see how good a job it can do just based on the lyrics. And the first question is, why lyrics again? There's this nice quote from Josiah Perry from our studio. So lyrics, again, music I think most people can relate to, like some kind of music. And lyrics can carry a lot of message and describe a lot of sentiments, as this excellent line from this song from LMFAO. So political statement clearly, as described here, taking another shot and turning up. But we're not going to use this. I think this is pop or something. I don't know what kind of music that is.
Yeah, something like that.
We are going to be using different genres. We're going to be using metal, because I like metal, basically, and nobody can stop me. But there's another reason as well. Like, metal fans have been classifying genres obsessively over decades and have very clear delineations between those genres, which are mostly based on some kind of musical identity between, say, death metal and black metal. But there are also lyrical themes, so we'll see if we can, from the lyrics, be able to classify between those three genres. And just to give you, if you know nothing about metal, that's fine, you don't have to.
I certainly didn't before I started this.
So just to give you like a little snippet from Wikipedia on each of those. So death metal, lyrical themes. Basically imagine an 80s B horror movie with a lot of, like a slasher movie. So it includes themes such as occultism, mysticism, or lots of violence, blood and gore. We're not going to show any of, or very little of the actual lyrics today. So if you dig into our data set, you might find upsetting things. So this is a content note. But also, just to be clear, they don't take themselves seriously. Again, like a slasher sort of zombie horror movie kind of vibe. But this is a theme. So a lot of violence, a lot of, let's say, this kind of stuff in death metal. Black metal has a very anti-religion sort of sentiment, especially anti-Christianity, and therefore satanic lyrics are common. But also other normal themes such as misanthropy, global catastrophe, war, death, destruction. But just to mix things up, power metal is the sort of the cuter one out of those. Has a lot of fantasy, mythology themes, so more positive themes. But essentially with those three, you can imagine that the difficulty will be mostly between classifying between black and death metal, because there's a lot of sort of similar, sort of a lot of overlap between the themes. And then power metal is one to be like, okay, it should be easier to classify this one from the other two.
Cool, thank you. So we're going to be using some standard R packages today and some less standard ones. So the first one is going to be tidy models. Hopefully everybody's heard of that one before. It's sort of the main machine learning framework package that exists within R. It's a really, really cool package, makes machine learning really easy, and that's kind of what the entire workflow today is going to be based upon. We do also have three other ones. So you see text recipes, text data, and tidy text, which are obviously just specific to the fact that we're going to be working with text data, i.e. lyrics, in this workshop. Cool, okay. Next thing to do is to head over to our studio. So if anybody's not got that open, please open up our studio. Ideally open up the project that you created following the instructions on the email, and then open up the tidy text classification.r script.
Let me do the recording thing. Okay, yeah, unfortunately you have to deal with this little bar at the top right here because Windows likes to be annoying.
Cool, thank you. Okay, so the first thing that we're going to do is I'm just going to start by librarying in the packages that we're going to be using throughout this session. So I'm going to library in tidy models, which is obviously going to be allowing us to fit machine learning models. Tidyverse, just your standard sort of data manipulation one. A couple of other cool packages in here that you might not have seen before. We've got CLD3, that's Google's compact language detector. Tidy text, which is going to be for pre-processing text data. Text recipes, which is going to intertwine nicely with tidy models, but again for text. And then some other ones that I think we're going to talk about more in detail when we get to those. So I'm going to start just by librarying those in. So I'm just going to highlight all of that and run it. And what I'm also going to do is I'm just going to run a large section of this just because it's going to take a little bit of time, and then I'll explain what we're doing after that. So I'm going to run here from lines 18 down to, let's say, down to 83. So that's 18 to 83 if anybody wants to do that as well. And then I'll just talk about what we're actually doing in each of these lines. Give you a second to do that as well. Cool, okay. So the first thing that we're going to do is we're going to read in the two data sets. So we've got the first one here is called tracks, and the second one is lyrics. So the tracks data set, remember Daniel talked about how we use the Spotify API when we were trying to collect these data sets. The tracks data set is the one that comes from the Spotify API. So the information that that's going to be giving us is things like genre, which is one of the most important things, obviously, because that's what we're going to try and predict. It's also going to be giving us things like valence, danceability, and some other cool metrics that, to be honest, we're not going to be really using today because we're going to be focusing on the lyrics. But it also gives us information like different tracks, what their genre was, what the artist name was, track name, and things like that. Then we have our second data set, which is lyrics. Now, this is the actual scraped lyrics that we got from all of those different lyric sites. So we scraped them using rvest, if you've seen that package before. And these came from songs that we found via Spotify. So we found songs on Spotify, we got the name of the song, the artist name, and then using that, we tried to find, say, a URL on these lyric sites and scrape lyrics off there. So we actually can match these tracks that we have in this tracks data set, which have a track name, artist name, genre, and a track ID, to lyrics that we have in this lyrics data set, which are going to also have a track ID, artist name, song name, but most importantly, the lyrics. And then at some point later on, we're going to join these two data sets together and then try and do some predictions. Okay, so the first thing I'm going to do is I'm going to bring up this lyrics data set. So I'm just going to type lyrics in here, and I'm just going to pop that out into the viewer. And just to have a look at this, this is the one that is, it's the tracks data set I should be looking at. That's the one that has the Spotify API stuff. Is that right? I'm looking for genre. Where's the one? Where's artist genre? Sorry, I'm looking for it.
It is in tracks.
I thought it was. I can't see it. Am I being stupid?
It's because you have already cleared it when you run the whole code.
Okay. Oh, no, that's annoying. Right, let's start again. Okay, I'm going to do this a bit slower now. I've run it too quickly and actually fixed the problem.
Just go bit by bit.
Yeah, I'm going to go bit by bit because I've actually just solved the problem I was about to show you, which is why it's not there anymore. So let's try that again.
If you go back on the pane, it's going to update.
Yeah, cool. Okay, so this was the original problem I was trying to show. So when we get the artist genres from Spotify, so this is in that tracks data set, we get many different artist genres. So you can see up here in this artist genre column, we've got really, really specific genres.
Just to be clear as well, like they have each track or each artist in Spotify, the genres are associated to an artist, not a track, but also has each artist has a variable number of genres. So to save that to a flat file, we just compress that into a single column using those separated with the two sort of vertical bars. So that separates two genres here in our data set. And as you can see, there's a lot of weird genres. That's Spotify data. I don't know if it's something they curate themselves.
Yeah, so you've got things here like Colombian pop, Canadian hip hop, all of this stuff that we're not really going to care about, and really specific types of metal that really we're not going to need. And so we're going to try and break this column up into multiple columns. In fact, we're going to break it up into artist genre 1, 2, 3, etc. until we've broken them up as many as we can. And then what we're going to do is we're going to try and find whether or not there was death, black, or power metal as one of those genres. And those are the tracks that we're going to actually bring in.
Can I ask a question about that?
Of course, yeah.
Probably something in regards to what happened before. In order to be able to get the lyrics, the actual lyrics, you say addresses, the URL where the lyrics were reported. Have you done that through sort of systematic assessment or website? Just a little bit of manual work, just to understand what is on the bench.
Yeah, so just to repeat the question, so it's in the recording. How did we get the lyrics URL, right, essentially? A lot of trial and error. That's why you will see that if you actually open the lyrics data set, we have about, I think, 50% of the lyrics for the track, 50% of the tracks have lyrics, because there's a lot of, especially in like pop genres, for example, there's songs that the title might be, X and then featuring Y. And then the URL might not have the featuring Y part. It's definitely not a very, trial and error.
Yeah. Yeah, you don't get 100% coverage, and yeah, it's just completely just going sort of manually and trying to get as many lyrics as you possibly can.
Also on metal, there will be a lot of instrumental tracks as well. Then you obviously try to find the lyrics.
And there's
I don't think
nothing
you will.
Okay, thanks.
Cool. So the first thing that we're going to try and do is we're going to break up this column artist genres into multiple different columns. Now, in order to do that, we're going to use the function tidyRSeparate here, which breaks up a column based on a separator. In this case, our separator is these sort of vertical bars here. And we're going to use this regex pattern that we actually have stored in a utils.r script. So if you looked carefully when we libraried in these packages, we also sourced a utils.r script, and in that we just had some regex, which we're going to be using here. So we're going to be separating out this column into multiple different columns using this particular regex. Now, what we need to do is you need to also give it new column names that you want to separate it out into. And in order to do that, in order for us to have the new column names, which are going to be artist genre 1, genre 2, 3, 4, etc., we needed to know what was the maximum number of genres that a track could be assigned to. Because you see this one, for example, only has 2. This one has, say, 6. And so we had to work out what the maximum number of genres are so that we could create those. So that's just what this line here is doing. And then we also get some column names. So max genres here is going to be 18. Genre column names is just artist genre 1 to 18. And then we're going to separate those out. Cool. So eventually we're going to have those as the different columns once we've run this line. Now we're going to move on to this section here, which is where we actually try and define what specific genre we're going to be looking at. So this is really where we're going to get the labels for our classifier. So the first thing that we do is we look in any of the artist genre columns. So that's what this code here is saying. It's saying if any of those columns that started with artist genre contain the value death metal, then we're going to give the indicator column is the genre death metal a 1.
Also, that will detect things like, I don't know, Canadian death metal or something like that. So exactly. That will be filed under death metal.
Exactly. And yeah, same thing with black metal, same thing with power metal. And obviously these aren't necessarily mutually exclusive. And so what we then do is we also filter out any tracks where we had multiple of these genres. And that's what we do here. So we do a row-wise, if you've ever seen that before. It just allows you to create a sum across different columns. So here, when we're doing ncats, we're just finding out how many of these 3 categories are ticked. And if the answer is not exactly one of them, then we're going to drop that row. So basically what we're saying here in this section of code is look for genres where we have death metal, black metal, or power metal, and only keep tracks where we only had one of them, so that we actually are working with tracks that are specifically death, black, or power metal, so that we can actually build a fair classifier.
Just also to set the scope of the problem, because we're doing single, that's where I always get, the terminology is not very consistent across the board. Different people use it differently. But we have if we didn't do that, because a track can be both death metal and black metal, they're like sort of fusion genres, if you will, that's very common. So you could have a multi-label classification problem. We're not going to do that. We're doing a single label, but multi-class, because we have 3 classes, so it's not a binary classification problem.
Exactly, yeah. So multi-label would be like you could have multiple classes. So, you know, one thing could be black and death metal, but we're doing multi-class where it's got to be mutually exclusive. It's got to be one, either black, death, or power.
And basically we're filtering songs that are more than one genre. So we're playing it safe, basically.
Cool, exactly. Next thing just we're going to have a quick look at is the lyrics themselves. So if I look at the lyrics dataset, and I look at the lyrics column, and I look at the first one, and let's just actually pipe this into cat, just so that we can actually read these lyrics. You can see that when we've done the scraping, we've ended up with some of these lyrics. We've ended up with extra information, for example, the verse, the chorus, in square brackets. And so what we do here is we just get rid of anything in square brackets. So I'm just going to run this line, which gets rid of anything like that. And you can now see if I run the exact same code again, those things in square brackets have just been removed. So we're now just left with just the lyrics so that we can actually use these in our classifier, and we're not getting things like verse, chorus. Okay, now this is one of the biggest steps here is we're actually now going to join the lyrics dataset onto the tracks dataset, and then we're going to be using this new lyrics dataset for the rest of the time. So we're not going to touch tracks again. So tracks really was just to get the genre. We've now got that, and we're now going to bind it on to the lyrics. And so that's what we're doing here. We're just going to do a left join, and we're going to drop any NAs. So any rows that contain any NA are going to be dropped. And that means that if we say had lyrics where there weren't any lyrics, that row is going to be dropped. If we had genres that were both black and death metal, we chose here that they would be NA, and so they're also going to be removed. And that's what this line here is doing. Okay.
Tracks that are none of those genres, like there's some pop and other stuff in our data set is going to be dropped, yeah.
Exactly. The next thing that we also wanted to do is we wanted to make sure that we were working with English lyrics. To be honest, you could build a classifier with any type of lyrics as well. It would work absolutely fine, but we just thought for the sake of this workshop, it would be more clear and would be easy to explain if we're just looking at lyrics that are English. So what we use here is a function from Google's Compact Language Detector. So that's this CLD3 package, which allows you just to detect language from a string. So our string in this case is going to be the lyrics column. Slightly confusing here, there is the lyrics data set, which within it has a column called lyrics, as we just saw up here when we catted it into the console. And so that's what this is doing here. It's detecting the language for each of the rows based on the lyrics, and then we're just going to only keep rows where the language was English, and that's what this filter is doing. Okay, so just to have a quick look at what our data set now looks like, this is the lyrics data set which we're going to be using from now on. We look at count here, which just shows you the distribution of a particular categorical column. In this case, the genre column, which is the column that we created, if you remember, just up here. So we found out whether things were death, black, or power metal, and then depending on whether it was black, we gave it black metal, etc. And we bundled that all into a single column, which is called genre, and that's what we're looking at here. So you can see we've got 2,000 rows for black metal, which is the smallest category, and then slightly more for the other two.
Yes, it has an imbalance, this data set, not big, but it does have, yeah.
Correct, exactly.
Right, so now onto some tidy models. So I don't know if has any of you ever used tidy model or not used tidy models? Is it relatively or maturing, let's say, framework? It's the equivalent of, let's say, the tidyverse for modeling, right, for machine learning. But as you'll see, it allows us to sort of frame things in a very nice way and to try lots of different algorithms or feature engineering techniques, all of that. So first thing we do is we do our usual split into a training set and a test set. So we save 70% for training, 30% for testing, and we stratify it by genre. So so we don't exacerbate the imbalance. The proportions between the genres are going to be maintained in each set, right? The training and the test set. The test set we're going to set aside, and I'm going to look at it much later only. With those functions here, training and testing, again, all of those functions are from different packages from tidy models. So we have our objects here. So for example, lyric split is what's called the split object. Again, all of those objects are defined. The tidy models will know, the different packages know how to work with those objects. But essentially, this is a subset of the original data frame. I should probably increase this a little bit here, and we don't need this. Probably better. So this is a subset of the original data set. So it's a tibble, a data frame, and so is the testing one. And we have about 8,800 rows in the training data set and 3,800 about on the testing data set. So within the training data set, we're going to further do subdivide. We're going to train things and assess them using cross-validation. So we're going to use a threefold cross-validation. So again, we get our training data set, we subdivide it into three folds of equal size, stratified by genre again. And when we do the training later, you see, or the fitting of the model, what this does is that we'll set one of those folds aside, train on the remaining two, assess the model on the third, and do that for each of the three subsets. or each of the folds. All of this in the training data set. We're not touching the testing data set, right? So we're following the proper protocol here.
Yeah. So yeah, just a quick question. Is everybody sort of familiar with the idea of splitting your data in machine learning and sort of why you do that? Why you have a training data set and a test data set, one that you touch? Mostly nods? All good?
No, that was, yeah. So, yeah.
Yeah, sure. Do you want to, sorry, after you.
Okay. Well, basically the idea is if you try to, you're familiar with like overfitting a model or so essentially what you want is your model to do as you know, if you train your model and assess it on the same data, it might do really well. It might just, if you have a model that's complex enough, you can just memorize your data, right? And just spit that back at you, and you've got 100% everything right, and then you show it some new data, and it's going to be really poor. So the idea is that the data that we use to train the model is not the data that we use to assess it or to have the final sort of, you know, this is the proper way to assess a model's performance is on data that it hasn't seen, essentially. That's the principle we're trying to respect here.
Exactly, yeah. So it's all about, you know, having strong predictive power. It's all very well. We can't just have a model that does well on the data that we already know what genre it's at. We want the model to be able to see new data. We don't know the genre, and it to be able to get it right in future, i.e. unseen data. And so we split into that training and test set so that we can actually see what would it actually look like if it tried it on data that it had never seen before. And that's going to be that test set.
Okay, so first thing we're going to do is we are going to, so the machine learning algorithms in general will only work with numeric data, right? Some of them work with categorical data or text data, or text, which you can consider categorical. But we want to transform that into numeric features, right? So one of the ways to do that with text is called TF-IDF, which is, I will explain in a second what that is. So we'll start by tokenizing our lyrics, which means we're going to split it every word. Each word will be a separate row in our data set. We're going to so basically the data set is going to gain a lot more rows. We're going to use this function from tidy text. They have such similar names, those packages. I'll show you the result is essentially now you see the same track now has multiple rows, whereas each track was a row before. And we created a new column called word, where each word of each song this is what's called a token in text analysis. And all of the other features have been just propagated right in those. So if we scroll down to so our data set now, the data frame now has 2,500,000 rows.
Yeah, what was it before? Like 11,000 songs, was it?
Something like that. Yeah, we got this 12,000. No. So this is just to show you what tokenizing is. This is if you were doing it sort of by hand. You know, we saved this in a separate data frame called tidy lyrics. I'll show you the tidy models way to do that. In tidy models, we try to break the analysis or the model training and fitting and predicting into two separate steps. One of them is the feature engineering and the pre-processing we do, all the modifications we do to the data set before we send it to a model to be fit. This is what's called a recipe in tidy models parlance. And you will be clear in a moment what's later on when we try a different recipe or a different model, why you'd want to do that, because it sounds like it's more work for now. If you have used in Python like scikit-learn, this would be like pipelines. The idea is you don't want to if I had a specific way to say I want to do this TF-IDF on my data set, I will transform the data set, and then if I wanted to try a different feature engineering technique, I'd have to load it again, transform it again, save it in a different variable. This way, we only transform the data and fit when we need it. Basically, so we're going to create a recipe here where this R formula essentially says we're going to try to predict genre from the lyrics column. We're not going to look at any of the other columns from the training data set. And step tokenize does essentially what I've shown you before. It's going to separate the lyrics into tokens, so each word. This step here is, so imagine how many words you're going to end up with, right, in the whole data set. So this means that we're going to keep only the words that are the 250 most common words in our data set, because otherwise we'll end up with a lot of features. I'll explain in a second what's the TF-IDF. Probably good to let this run here for a second while we do that. So TF-IDF stands for Term Frequency Inverse Document Frequency, which is, it tries to balance two things. So term frequency is how often a word occurs. So you want your words to have, let's say, your numeric features associated to a specific word. You want that to be higher if that word occurs a lot. That's probably means it has, carries more signal, let's say. But inverse document frequency takes into account if a word occurs in many of the songs, that means it's probably not very good for helping the model to classify between them. So we want words that are frequent only in some specific sort of documents, but not only in. It's a balance between both, right? If you get, so for example, if you use the word the, it's going to be very common across the board. So the term frequency is going to be high, but the inverse document frequency is going to penalize that, and therefore it will. So it tries to find a balance between both. And what this does is probably the best is to rerun this here. So here we created a recipe. Again, with those three steps: tokenize, limit the number of tokens, and then TF-IDF. All of those are from the text recipes package. It has a lot of conveniently, everything is there for you already. So you have a lot of options to do feature engineering in text. Very convenient. What we do after here, so this only defines a recipe. So if you have a look at what it is, you see this is something from Tidy Models. This is a recipe, has one input variable and one output variable, and one predictor, which is the lyrics column, and one outcome, which is the genre. And then it does have some description of what the operations are. But this in itself doesn't really do anything for now. Just to illustrate what that actually does, we can, again, Tidy Models parlance, prep and bake the recipe, which means this will show you how the transform data looks like. So I will run that again just to show you what this looks like. Essentially, the result will be one row for every song and one column for each of those words. So each of the features will be the TF-IDF scores for specific words in our data set. So again, in text analysis, this is usually referred to as the corpus, is the collection of all your documents. In this case, a document would be the lyrics for a specific song. The corpus would be the collection of all our lyrics. So, for example, this TF-IDF lyrics A means, again, those names come from text recipes. The TF-IDF underscore lyrics is the name of the column, and then the ending is the actual word, so the word A. And then for each of the songs, again, we have 8,800, we'll have the TF-IDF score for that. That's how we get the numerical features. And you can go on the documentation for this too. You have options. There are multiple ways to calculate that. It's all well documented. But essentially, what you need to know for now is just TF-IDF is a way to get numerical features from text. And if you see here, we have 251 columns. So one is our target, the genre, and then the other are the 250 most commonly occurring words in our corpus.
And that's because we did that step token filter, right?
Yeah.
Otherwise, we would have every single word that existed across all the lyrics. But we thought that would probably be overfitting, probably too much. So we limited it to the most.
You would end up with a model with thousands and thousands of features, which
would be too much.
Yeah.
So we keep it to the top 250 most common.
Okay, so again, Tidy Models. In Tidy Models, we have what's called a workflow. A workflow is a recipe which deals with all the data manipulation processing, and then a model. Both of them together, we haven't added a model yet, but both of them together make a workflow, which is essentially like a pipeline from data to predictions, right? If you got the data processing and the model fitted, then you can. So we're going to create a workflow, just like this creates just an empty workflow, and we add a recipe. We add our TF-IDF rec recipe, and again, this here, if you have a look at it, it's just some kind of tidy models object. So yeah, see, we have a preprocessor, this recipe. We don't have a model yet, and our recipe has 3 steps. As a first model, like a quick baseline, we're going to use a naive Bayes model. Those functions, again, this is the standard way of doing the way of doing things in tidy models. You have this function such as this naive Bayes. It's just a specification of a model. We haven't specified any parameters, anything. This is all. One of the good things about tidy models is it provides a consistent interface across all sorts of different models that might come from different packages, but it provides a way to sort of use them in a consistent way. So if you wanted to change the model, for example, you still use a workflow, then any function that we use as a workflow will follow through in the same way. Whereas if you were dealing with the models directly from the packages, their API might be very different, and you might have to tweak your code all over the place to make it all fit together. Well, that's one advantage of tidy models. And you'll see later as well, we'll change the models, we'll change the recipe. It's very easy to do that. So naive Bayes model is essentially it relies on a very strong assumption, is the independence of the features, which, if you remember, our features are the TF-IDF scores for different words. So the assumption that the words are independent from each other is a very strong assumption. So this model would just be used as a baseline. It's quick and dirty and gets you a result that probably you can't do worse. But it works reasonably well for text. Better than it should, really. And now, with our workflow from before, we're going to add a model to it, our naive Bayes. And if you have a look at the workflow object, now it has a little extra bit. This was here before. The model is now naive Bayes 1, and that's the specification of the model. And now, since we're using cross-validation with our folds, we need to use this fit resamples function. So it will fit the model using cross-validation to the training data set. Again, lyrics folds is the 3-fold split that we use for cross-validation that we did before on the training data set. And so fit resamples take a workflow, the folds, the cross-validation folds, and then this option here is just so we save the predictions because we're going to use them later. So I'll run this now. This will actually fit the model. Take a little while. There's a good moment for questions.
Yeah, great time for questions. Probably got about 40 seconds here while this fits.
Just in case anyone's computer starts running out of battery, I forgot to mention at the beginning that we have extension cables, and there's plugs on the right and on the left that you can use an extension cable to plug you in if you need. So just give a shout.
Okay, we've finished fitting our model. So we call a couple of functions again whenever I'm not mentioning where a function comes from, it's going to tidy models or one of the packages that we talked about earlier, tidy text recipes. So to get the performance metrics, we have to use this function here, collect metrics, and then collect predictions. We'll save the predictions we will use in a second. And you might be looking at that and seeing, oh, there's a lot of let's say a lot of overhead, like, oh, I can't just get the metrics, I have to call a specific function. There is some overhead, but again, you'll see later when we change things, everything remains the same. We want to change recipe, we want to change the model. So the metrics that we get is, by default, get accuracy, again, multi-class accuracy of 57% or so with the naive Bayes, which means that it's predicting the correct genre at 57% of the time.
It's okay.
Which is, again, for a baseline, it's not too bad. Here, n equals 3 because we got the 3-fold validation, so we get 3 accuracy values, and then this is the mean value, and this is the standard deviation. And then this is the area under the rock curve, which I'll show you later what that means. But this is a surprisingly good value for something for a model so simple and very basically no feature engineering, just TF IDF, not removing stopwords, nothing. It's as simple as it gets almost. I don't know if you have seen a confusion matrix before. This is essentially, so on the vertical axis we got what was actually predicted, so the three classes, black metal, death metal, and power metal, and on the horizontal axis the actual class. And so if we're predicting correctly, it's going to be on the diagonal of this kind of matrix, right? We want the true black metal to be predicted as black metal, and this is the number of times or number of cases that got predicted into that class. So you get this non-integers because it's averaged across the three folds. But we're almost never predicting black metal. Remember, we had like 2,000 black metal songs, and then 70% in the. So it's almost never predicting. If you look at the black metal row here, that's almost never predicting it. And then the other ones, so it's predicting a lot more death metal and a lot more power metal, which is unsurprising. Like the difficult bit is going to be detangling sort of black metal and death metal from the lyrics, because again, thematically, that's a lot closer than power metal. So it's kind of what we expected. And yeah, so for example, power metal is doing relatively well, or death metal is probably the one that's doing the best. And we can actually plot the ROC curve. So, okay, who here has seen a curve like this before, or has not seen? Robbie's, I imagine, yeah? Or no? Okay.
No.
So, this is a standard, a common way of looking at the performance of a classifier. Let me, actually can't see I think there you go. So the vertical axis is it's called sensitivity. It's essentially how sensitive you are to getting the true positive cases, the ones that, so let's say for each of the classes, so for the class power metal, the sensitivity is going to be for actual power metal songs, how well your classifier does on how often does it predict the ones that are power metal to be power metal. And then on the x-axis, it's kind of equivalent, but for the negative predictions. So for power metal, again, when a song is in power metal, how likely is your classifier to predict it not being power metal? And those classifiers, you don't get a categorical output. You get a numerical output generally. If you have used logistic regressions, for example, it gives you a probability between 0 and 1 of something belonging to a class, of a specific instance belonging to a class. And let's say, imagine you get a value of, 0.5 or something. So again, probably a number between 0 and 1, and you have to have a threshold for so if you're doing binary classification, so classes A and B, you have to have a cutoff of which you say, well, above 50%, for example, it's going to be class A, and below is going to be class B. And that threshold can be varied between, again, 0 and 1. And this is how you produce that curve. If we start all the way here, at the bottom left, we always predict things to be negative, basically. This classifier is completely useless. Any classifier actually in the diagonal here is completely useless. Or it's a coin flip. It doesn't do better in coin flip. But so here we predict everything to be negative, and that's why we get a sensitivity of 0. And at the other end, we predict everything to be positive, no matter what it is, or to be that specific class. And then we get 100% sensitivity, but 0 specificity. And obviously, what we want is a trade-off between both. And what you really want is your curve to kind of go like this, as close as possible to here, and then go to, because those ends are fixed. And that's why the area under this curve is a commonly used measure for, because this is a 1 by 1 square. If you got an area of 1, then your classifier is perfect. And if you got an area of 50%, then your classifier is a coin flip. This is a multi-class equivalent. So here, like the ROC is usually defined for 2 classes only for binary classification. This is an extension for multiple classes. And so as we vary the threshold between the different classes, to classify either one way or the other, we get different points in the curve, and that's how a whole curve is produced, by varying the threshold from 0 to 1. And we do that for every one of the classes, and that's what we get here. So essentially, power metal is doing a lot better, because again, the area under the curve is higher, right, as you can see. And then it's relatively similar for black metal and death metal. Again, this is what we expected. Sort of out of the box, power metal is going to do better because it has more distinct lyrical themes. So we are not surprised by this.
Is it worth doing a really quick summary of what we've done before we go into the exercise? I think we've probably got time.
Yeah.
Just a really quick one. Do you want to do that, or you want me to do that?
You can go for it.
Sounds good. Cool. So just to really quickly sum up, so we had information from Spotify, most importantly the genre in this tracks data set. We had lyrics that we scraped online. We did some pre-processing of the lyrics. We then got a column called genre, which is going to be black, death, or power metal. Then we split our lyrics data set, which now has the genre and the lyrics, into training and test sets. The test set we're not going to touch until right at the end of this workshop. And then we created a training set as well. Now, in order to actually choose which algorithm we're going to use and to do things like hyperparameter tuning, we also need to split our training data set even further. And so we do that using cross-validation, which is what this vfold CV function is. So these are our folds, and that's why each of our confusion matrix, for example, is divided by 3, because we created 3 different folds within our training data set, and that's what we're using to evaluate the performance of our classifier. We looked at how we can convert our lyrics, which are full character strings with spaces and commas and etc., into individual words by unnesting the tokens, is the terminology. And we can do that outside of tidy models by using unnest tokens, just to do it in a data set, or we could do it inside tidy models as part of our machine learning workflow. And to do that, we define a recipe, just because that's what tidy models calls it. And the equivalent to unnest tokens is your step tokenize. And we also then, now that we've got each of the words for each of our songs, we then also try to create a numeric feature for each of those words that we're going to use. So we look at the top 250 words, and then for each of the words in each of the songs, we calculate a TF-IDF score, which gives us 250 features, obviously one value for each of the songs that we're going to look at. We bundle that pre-processing together with a algorithm into a workflow. So we create a workflow that has both the pre-processing recipe and the algorithm itself. We fit to each of our folds so that we can fairly compare within that training data set. And then we collect out our metrics and create some nice plots. Okay, so next up is an exercise. So we'll give you sort of 5-10 minutes to try and get on with this. The instructions are here. I'll leave them up. If you do finish early, there are answers that are in the answers folder. If you go to files and just click on answers, they'll be there if you want to have a look. But basically, you're just going to be trying to sort of copy the code and adapt it so that we're now fitting a random forest instead of a naive Bayes classifier. So yeah, give you 5 or 10 minutes to get on with that. Cool. All right, we're going to get started again, everybody. Hopefully you've all had a little bit of time to try and attempt that one. There's actually not too much to change, so just quickly reading out the questions. Keeping the same recipe, now try fitting a random forest with the random forest engine. Make sure you use the resampling folds as before. And then we're going to compare this model to the old one and then create a confusion matrix for the resamples. So pretty much the beauty of using tidy models is that all the code can just stay pretty much the same. The only thing that we're changing is the algorithm, and so that's the only thing we need to change in the code, which is really nice. And that's the whole sort of point of it, is that you have this sort of common interface to multiple different algorithms from multiple different packages. You know, this rand forest one, which is the solution to this exercise, comes from this package random forest. And that's what kind of really we mean when we say we set the engine here. But you just change this, really simple, random forest, engine is random forest, and everything else can just stay exactly the same. We add it to our recipe, we fit on the folds, giving our new workflow, and we then can just collect metrics in the exact same way. and hopefully everybody got reasonably similar results. Might be slightly different. It is a random forest at the end of the day. But yeah, we got much improved accuracy here of 0.71. So 72% of the time, we're able to predict the genre among the three correctly just by looking at those lyrics. Okay, so the next thing we're going to talk about are stop words. So we had a question earlier on about the word a and things like that. That's not going to carry much predictive power, is it? And the reason for that is because it's what we call a stop word. So there are words in the English language, like prepositions, for example, that don't really add to the meaning or aren't going to be useful for us in trying to determine what the particular text is about, but they still exist within the lyrics. And these are called stop words. So we're going to try and remove those. And the easiest thing to do is just to get a massive list of them and then just remove them.
There are packages that give us predefined lists. And again, you can go on the documentation of, say, this function stop words get sources, for example, from the stop words package, has precompiled, so well-established lists of stop words for English or for other languages, yeah.
Exactly, and that's exactly what we do here. So we get all the sources of stop words. We only keep those where the source was in English. So we do stop words get language, which is going to get the language, and only keep those that are English. Fine. But essentially, we are going to just have loads of different sources, and we're going to get all the stop words from all of those different sources. So we've got a massive list of stop words, and then we can just get rid of them. So if I have a look at this, this produces a data frame where we have a single column word and 1,300 different stop words that we're just going to remove. And in addition, we can actually add our own ones. So we obviously are going to be working in lyrics, and so there are specific, I think Daniel put in the comment here, vocalizations, which are basically just these type of words that obviously are not going to be useful for us in our classification.
Generally, like, so if you have specific applications with text, you generally will have, you will know what your stop words are. Or there's a lot of trial and error. You might go back and forth, like you fit a model and you see, oh, it's picking up a lot of, lots of words that are not going to be useful. You remove there. You can add them to your stop word list. Because the predefined ones are not going to have anything specific to lyrics, for example. Yeah,
and it'll be the same no matter what type of, what type of documents you're working with. You're going to want to remove document-specific stop words. So that's what we do here. We just add on an extra row, and then later on, we're going to actually need this not as a data frame, but as a vector. So we just pull that out. So we've got stop words vec, which is a vector, and my stop words, which is a data frame. Now, if we actually want to have a look at the effect of this, let's have a look at this tidy lyrics data set. So remember, this was the one that we pivoted longer. So each row actually defines an individual word. So this is all of our lyrics, but pivoted longer. So it's like 2 million rows or something like that. If we just do an anti-join with our stop words that we've got here, my stop words, if we just do an anti-join with that, we're basically just going to filter out the rows where that was the word. And so we're going to get rid of those rows. So that's what we do here. And you can see that the number of rows in that data set has been reduced to a very nice looking number as well, somehow.
Yeah, less than half, really, less than a million.
Yeah. Cool. So again, we're sort of showing you how you can do that just in a data set if you were just going to go do some analysis. But again, we're working in tidy models here. So we're going to show you the tidy models approach as well, which is, of course, this is pre-processing, so we do it inside a recipe. So define our recipe as before, tokenize, so that's almost like that pivot longer, so that we've got different types of, we've got a word for each of the rows, and then we can just do step stop words, and that's going to be removing our stop words for us, and we just give custom stop word source, and we just give it this time as a vector, just because that's what it wants. So instead of using a data frame, we just pulled out that vector. And again, everything else is the same. We can now pick up just the best tokens, the 250 most common, and we're just going to create our TF-IDF features just as before. So I'm now going to prep and bake, which is basically just me applying.
Just making it wider, because there'll be a lot of...
Yeah, good idea. Just going to prep and bake, which is just applying those pre-processing steps, just so we can see what they look like. And this top data frame here is before we applied the step stop words. So this was our original recipe.
It's the same results from before, yeah.
Same results as before. So TF-IDF A We've got TF-IDF scores for an, and. But now after doing our stop word recipe, we get this data frame. So now we're only getting words that are actually useful, and those are going to be the ones that actually define the features. And so hopefully we're actually going to be using more useful features than we were before. Okay, so we've now got a new recipe. Again, tidy model is really easy. This is the only thing we've changed, and so all we need to do is just update our recipe. And that means we need to update a new workflow. So we add on our recipe to a new workflow, TF-IDF SWWF. We now are going to settle on a random forest because we just showed in the previous exercise that the random forest outperformed the naive Bayesmon, so we're going to be using that one from now on. And so we add those two things together. We've got the recipe and we've got the model specification, add them together into a workflow, so that's all bundled up into one big model fitting thing, and then we fit them to each of our cross-validation folds. So that's using this fit underscore resamples, just as we did before. So nice and easy. This again is just going to take a little bit of time to run, and then we'll collect the metrics, just as we did before, collect underscore metrics, and we can compare them to what we got previously. So if I scroll up to have a look at the results from the exercise, we got accuracy of 71.7% and a ROC AUC of 0.862. So that's what we're trying to beat. Cool. Okay, we have now fit that model, so that just finished. So where did we get to? So we just run fit resamples again, and just as before, we can now collect our metrics. And we actually see we get slightly worse results somehow. So not 100% sure why. It might just be that some of the stop words that we actually saw were particularly useful. Maybe we thought they weren't going to be, but they were. Our accuracy scores are slightly lower, and our ROC AUC scores slightly lower.
Very slightly. It's essentially the same result, yeah.
Yeah, basically it's not really making much difference, but arguably it's slightly lower. And again, we could plot another confusion matrix as well, which looks like that.
Yeah.
And you can see, it's kind of similar results. If you did plot one originally for that random forest, you can now see as well that it's doing slightly better. At least it's actually predicting some black metal now. And yeah, it's doing slightly better. But yeah, the stop words isn't really helping too much with this particular model. Cool. The next thing we're going to talk about is stemming words. That's another technique that you might use. Again, it's just kind of sort of trying to reduce noise. So there are functions, for example, word stem in the Snowball C package that essentially apply a stemming algorithm to any words that you have. And the idea is that you have lots of words in the English language that maybe have a slightly different ending, but really mean the same thing. So you might have, for example, happiness, happy, feeling, feel, something like that. And they all really carry the same thing, but they're going to be categorized differently. If you say, for example, feeling and feel came up quite a lot, they're going to end up in two different columns when you do your TF-IDF because you're looking at them as two different words, which is not really what you want. And so it might be an idea to actually stem those words using one of these algorithms so that those things actually come up as the same column because they really do mean the same thing. So just to give an example about how this function might work, if I run word stem on happy, it gives me back happy like that, feeling, feel, and you could try this all day with lots of different types of words, but that's really all it's doing, is just stemming it down.
It's trying to reduce to the root of the word, like if it's a verb conjugation or the feeling to feel or does to do and so on.
Exactly. And that just works on a vector, so we're just going to use it inside a mutate call. So I'm just going to say, okay, I've got my tidy lyrics, and I'm going to create a new column called word stemmed, which is just going to be applying word stem to each of the words. So you can now look at this data set. And if we scroll along all the way to the words, you can see how some of these have been stemmed using that stemming algorithm. Cool. Now, as always, we've sort of shown you how you do that on a data frame, but also this is actually something that you can do within tidy models. And we're actually going to kind of leave it up to you guys to work out exactly what that might be. So using some of the things that we've seen before, what do you think we're likely going to be able to need to do in order to try and stem our words as part of our pre-processing? So we're going to go on to exercise 2, which is going to be to fit another random forest model, but this time add in a word stemming step to remove the stop words that we had before. So we're going to do that as part of tidy models. And then again, just compare your results before. So again, give you probably 5 to 10 minutes in order to do this one. And as always, if you've got any questions, now's a good time.
Sorry if you haven't finished, but we kind of got to keep going to get to the end of this, but there's very little variation, and also you're probably waiting a lot of time if you try to run this because it takes a while for it to fit. But essentially we have a recipe as previously with tokenized stop words.
Record, sorry.
Yes, thank you. You will want this if you're seeing this later. And all we did is add the step stem, which will do the stemming of the words and then filter the tokens. It's a good idea to do stemming before filtering tokens because some of the, say for example, doing, do, done will all be mapped to the same stem and therefore might be filtered. So you would want to apply that before you're filtering the tokens, as we're doing here. If you did it the other way around, you'd get different results. And then TF-IDF, and then we define a workflow, adding a random forest model as before. Again, with the recipe and the model, and we do fit resamples on our cross-validation folds. Same thing as before, collect the metrics and the predictions. We're not using here because we're not plotting the ROC curve. And just to compare with what we got previously, so we got 2 sets of results here, which I printed to the console. One of them is removing stop words and stemming, and we get about 73% accuracy. And this is our previous one, same model, random forest, but not removing stop words, not stemming. And we got 71.7%. So we got an extra percentage point here, not a very marginal improvement, but an improvement nonetheless. So next thing is we're going to produce some variable importance plots for a random forest, just to see what are the words that actually the model is finding the most useful to make its predictions, where it's relying on the most, which features, right? And we do need to fit on the whole training data set, just because the package we are using, VIP, which has this function, VIP, which stands for variable importance plot, takes a fit. This function takes a fitted random forest and then produces that plot. It doesn't work with fit done on the that we did here with fit resamples, which fits on the cross-validation folds. We'll fit 3 models. So all we do here is just do a simple fit on all of the training data set. Just to, again, this would just be used to show you the variable importance plot. I should have set this to run before. Well, while this is happening, I'll just explain why we do this bunch of code here. All we're doing, we're going to show you for the different classes. So the model makes we're going to make the predictions on the test set on this fitted model. So each of the class, and then for each of the classes, we're going to look at the most common words per class, just to show you, is it capturing anything about, remember what we've seen before about some of the lyrical themes of the different styles? Just to see, is there a chance this is doing something actually what we expect? It is clearly doing something. It's classifying things, in a reasonably well, surprisingly well actually for such a simple model. But it's always good to do some sanity check. Are the predictions being good because of what we would expect? Okay, maybe we won't keep waiting for this. Yeah, we can show this at the end. Do you
No.
know how long this takes?
It's not supposed to be more than like 40 seconds, but yeah,
Maybe.
we can move on. I
Maybe
reckon.
R is getting tired.
Yeah, I think so. It's had a long day.
It's a shame because this is we should have saved that block. It was worth waiting. There you go. This is our. So we are showing the 10 or something, 10 to 15 top. So what this means is each of again, those are the features. Remember, they start with TF, IDF, underscore, lyrics, underscore, and then the actual word. And those are the most, again, something for variable importance for a random forest is essentially a measure of how useful that specific feature was for the model to make its predictions. As you can see, some of the words like death, flesh, probably all of the death metal, blood, but also you got some stuff like a time or a light, day, fight, which probably come from the power metal. So again, this is not per class. We train one classifier for the 3 classes, right? So that's why you got everything mixed up here. It's not separated by class. But just to show, okay, this on a sort of first kind of sense check, it does make sense. And then, no, I shouldn't have done that. Those are going to be, again, for the predictions that we made on the test set, the most common words for each of the genres. So black metal, death metal, power metal. Again, for black metal, it's going to be, again, night, blood, light, black, cold, all the expected themes, although we don't see any kind of anti-religion sentiment here. But for death metal, it's definitely flesh, blood, death, and so on. And for power metal, again, maybe some of those fantasy themes like fight, sky, night, light, heart. So again, this is just to illustrate. So we've shown you so far one feature engineering technique, or main one, TF-IDF, again, very common in text processing. We're going to do another one, which is called word embeddings. So this is a lot more, is a lot more abstract, but it does get very good results. So I will flick back to our PowerPoint here, just have a little slide on this. So we are using pre-trained word embeddings. So the idea is word embedding is a technique to associate to a word a numeric vector. How we do that, I'll talk about in a second. But we use pre-trained word embeddings. You could train your own, but there's a lot of sort of pre-trained sets out there that are trained on really large corpus of data. For example, all of Wikipedia, that kind of that magnitude of data set usually is used, and they can be very complex using neural networks and all of that. We use the glove ones, which is a quite old one, but you might have seen this result here on the bottom right. The idea that it's a very sort of classic example in word embeddings. So imagine, we're trying to find a technique to assign, for each word we assign, for example, a vector of 50 dimensions. And our technique is intelligent enough to, for example, it's going to look at the context of words that occur around a certain word. It's going to try to capture some of the semantic meaning of the word, the relations between the words. And we're going to somehow map that to this abstract vector, right? But the interesting thing is that, so in this classic example, imagine here you plotted this vector space here on some vectors for certain words in this graph here on the bottom right. So you have the vector for man, for example, the vector for woman, and if you take the difference between them, so woman, you subtract man, you get this difference between them both, and you add that to the king vector, and the nearest word is queen. That's like a classic example in word embedding. So you're capturing some of the semantic meaning in that the difference between those two words will be some kind of gender difference. If you start from king and you add woman, subtract men, again, in those abstract vectors, the nearest word, if you'd want that to be queen, right, the nearest word. So if you're trying to capture, again, some of the relations between the words, and it allows you to do those mathematical operations on it. Also, just quick word of warning, of course, all the biases in your data set are going to be reflected there. So you might get a lot of sexist assumptions about, what's associated to women or men, but that's something for another workshop, perhaps. So now we're going to look at some lyrics. This beautiful song here, Horrendous Memberman. Let's not read the lyrics too much, but so just to show you, this is a song, well, you get everything you need to know from the title. There's a lot of torture and violence. So we're going to try and use word embeddings to see, can we find the most similar lyrics and the least similar lyrics in our data set to this song, using word embeddings. So this is what we're going to try next with our glove embeddings of the glove 6 billion embeddings. If you haven't downloaded this, it will be a long download, so maybe leave it for after. So the idea is the 6B stands for 6 billions. It was trained on 6 billion words, or a corpus of 6 billion words. And it has vectors for 400,000 different words. So this is a data frame. Again, this comes from a package, pre-trained. We didn't do any of this. Essentially, for the word the, then you have 50 other columns, so that's why you have 51 columns with those values of those vectors. So this is the vector associated to the word the. And in the same way, you got for 400,000 words here, you got a word embedding. Each of the dimensions will be a value between -1 and 1. So what we're going to do here, well, we did this before, is our tokenizing of the lyrics. Again, separating each row is one word. And we are going to join that to so we're going to join the word embeddings to those words. So each of the words that has a word embedding is going to get those 50 dimensions. And we're going to average across a song. So the vector for each word in a song, we're going to average, and we're going to get a vector associated to a song. It's kind of like the average, vector for that song. And this is what we're going to try and use to characterize the song and see which ones are most or least similar to that one. And we'll see if that works. It takes a while. I'm going to run through this.
Yeah, I'd run a little bit further because it's going to...
Yeah, let me run it first because it does take a while. And then from that, we're going to use something called a cosine similarity. So we have vectors, and essentially is a measure between 0 and 1 of how similar they are. The closest it is to 1, the highest it is, the most similar they are in that 50-dimensional space again. And we're going to use that to compare. So let me show what that looks like here. This is probably best to show it this way. So track ID, the track name, and then this is the each of those columns here is for this song how similar it is to the first song, the cosine similarity with the first song, the cosine similarity with the second song, and so on. And as you can imagine, since the maximum similarity is 1, the diagonal is going to be 1. If you think of this as a matrix, this part of the data frame, and it's going to be symmetrical as well, because, well, the similarity of the first song to the second song is the same as the second song to the first song, because we're using a good or a reasonable metric for this kind of comparison. And so this is a couple of functions here from our utils package. We won't have the time to go into, but essentially it's just from this data frame that has all the cosine similarities between the different songs, again, that have been computed with the average word embedding for that song. We're going to find the most similar ones and the least similar ones. So the most and the least similar songs to that one from before. And it looks like that does. So our results here are the top 3, the most similar, and the score, the similarity score. Again, remember this is between 0 and 1. So 962, very similar. So they all talk about, well, violence and torture and so on. And the least similar ones don't talk about it at all. We can look at the lyrics, but just from the titles, you can see, okay, this looks like this is doing something. Even though this was a very, again, those vectors have been trained not in this data set at all. Like the 6 billion vectors, they are trained on the Wikipedia all of Wikipedia from 2014. So it's surprising that this works actually. And yeah, if you want to look at the lyrics, you can see, we again won't have the time, but there's like one of the least similar songs, for example, talks about rum. Yeah, some kind of pirate metal, I don't know. But yeah, it does work. So why are we showing all this? Well, this is just, again, to introduce word embeddings and doing things a bit manually, but we can actually easily add that to a recipe because text recipes has a step word embeddings. So everything being the same as before. Only thing to note here is that we can choose a bunch of different embeddings, and some of them, there's like larger versions of the glove embeddings trained on a lot more data. There'll be a much larger download. And this argument here is how are we aggregating the word embeddings into a single embedding for each document or for each song? We're using the mean as we did above, but you have other ways of doing that. Have I run this? Yes. Okay. So let's see what that looks like.
Or I can run all the way down as well because you're going to fit and stuff.
Oh yeah, I'm going to send the fit here just to... Yeah, I'm going to send everything. So we are first going to see just what is, again, as done before, what those embeddings look like, what this recipe looks like. You will get this warning. Oh, this warning is new. It's not the same one I was expecting. I don't know. I'll assume everything's fine. Is it because I have another window? No.
I think it's some plotting window being small or something stupid.
Okay.
Things get weird.
But the point is, so those embeddings, again, this is the transform data set from the, just to show you what the recipe actually does. Again, 51 columns in our data frame. One of them is the target, is the label, and the other 50 are the 50-dimensional word embeddings for that song, the average word embedding. So the recipe does what we expect it does, right? And then, well, it's still fitting. But just to show you, the code is copied, so you look, but it's essentially the same. We define a workflow, we add a recipe, we add a model, which is a random forest from before. We didn't even re-specify, it's already specified. And the results we get is, so we get 73%, which I forget it, so we had around 71, 72, but this is a model with 50 features. So the other one had 250 features. So this is capturing, with fewer features, actually capturing more of the signal, really, it has more predictive power. Yeah, so next, the confusion matrix. This is looking like the major issue we had before is being at least partially solved. We're predicting a lot more black metal when it actually is black metal. But one of the sort of choke points is the distinction between black and death metal. There's a lot of black metal that's predicted as death metal. Again, this is because, well, those genres, they have a lot more of a musical identity, let's say, than lyrical identity. So that it is normal that we'd find that the algorithm would have trouble with that. And the ROC curves, which are looking, well, I don't know if you will remember from before, but they are looking like they're going a lot more in this direction, which is what we want. We want a larger area under the curve. And as previously, power metal does better than the other ones, but we also got now death metal kind of taking off a little bit. So that's all good. We have another exercise, which is, well, it's just a little discussion. Maybe I'll ask the question if you can give me your answer. So the question is, what would happen if we refit the model and did a variable importance plot using the word embeddings? So instead of using TF-IDF as before, I don't know if you remember the plot, this one. What would that look like if we use the word embeddings, and what would be the problem with it? I mean, I can actually do it. I can leave it running while maybe somebody wants to attempt an answer. Yeah, it will. Yeah, exactly. The results will be like, oh yeah, dimension 7 will be a great dimension, and then you'll be like, oh yeah, well that means nothing. It's completely abstract. Whereas here, it's actual words. So there's a common trade-off in machine learning, sort of between often between performance and interpretability of your models. Okay, I hand it back
Cool.
to Andrew.
Thank you very much.
There you go. Dimension 7 is great,
Yeah.
I told you.
Exactly. Cool, yeah, we've got about 5 minutes left, so I'll try and rattle through the next bit as quick as possible. I don't want to keep anybody from food and beer as well. So the last section is just on hyperparameter tuning. This is the last thing that you would do when you really you've decided exactly which features you're going to use, you have chosen the best algorithm, and you just want to squeeze that last maybe 0.5% out of your model, and that's tuning your hyperparameters. So what we're going to do is we're just going to use the same sort of recipe as before. So we're just going to use our word embeddings. And what we're going to do now is when we define the model specification, instead of just leaving rand forest sort of like this, which is just a standard random forest model specification, we're going to give some of the hyperparameters that exist for the random forest model, and we're going to give them this placeholder, which is just this function tune, which basically just says, don't set this hyperparameter yet, I'm going to tune it. Now, what are these hyperparameters? We talked a bit about what the random forest actually means. mtry is the number of feature columns that you're going to choose for each of those decision trees. So remember we said you calculate many decision trees and each of them is going to not use all of the features but just some of them. Well, how many is some of them? That's what mtry is, and we're going to tune that. And then also, how many trees do you actually want to fit? You obviously might start to overfit if you create too many trees, so that's another hyperparameter that we're going to tune.
Also takes much longer, yeah.
Yeah, exactly. Now the question is, what are we actually going to tune them over? So, how many, what number of columns are we actually going to try out? Are we just going to say try, we've got 50 feature columns. Do we say we want to try each decision tree, trying maybe one of those columns, and then maybe 2, 3, 4, all the way up to 50? Well, actually, we think that'd probably take too long. We think maybe one feature column per decision tree is going to be absolutely useless, so let's not even bother trying that. So really what we're doing here is we define a hyperparameter grid to tune our hyperparameters over. So we've got 2 hyperparameters, mtry and trees, and here we just define a evenly spaced grid in that hyperparameter space of those 2 different hyperparameters. So we set levels equals 5 here, which means we're going to try 5 different values for each of those hyperparameters. And obviously we're going to try all the different combinations between them. So 5 times 5, we're going to end up with 25 pairwise combinations for each of those hyperparameters. So we're going to try this as a single model. We're going to try the next row as a single model, etc., etc. We're going to compare them all within our cross-validation folds, and we're going to pick the best one. So again, we just create a workflow. The only difference here is that we're using now this tune specification, which remember was the one that had our placeholders in it. We then actually, to run our tuning to actually fit the model, instead of using fit resamples, it's just a different function. Inside tidy models, you now need to use tune_grid, but it's exactly the same. You give your workflow, you give your folds, you give any control like saving the predictions, but the extra argument is that you now give your hyperparameter grid that you want to tune it over. That's the only difference. Other than that, it's exactly the same. We don't run this here because you are literally fitting 25 random forests. It's going to take ages. You saw how long it took to just fit one of them. So we're just going to read that model object back in, and then we're just going to collect the metrics from it. And you see when you do collect metrics now, you actually get not just a single score for accuracy and ROC AUC, but actually one for each of the pairwise combinations. So we get a 50 rows here, i.e. accuracy and ROC AUC for 25 different combinations. And you can see some of them are actually doing quite well. There are also some nice, autoplot is a good function within tidy models. It works on lots of different types of objects. Often it's just good to try. It also specifically works on tuned hyperparameter model fits. And it gives you a nice plot here, which I'm not going to dwell on too long, but it basically just shows you over your different hyperparameters how your model metrics are changing. So that's what you can see here. And again, not going to go too much into this. The main thing to note really is that look at the axes here. They're not really changing too much. They're very, very similar. It's quite a small axis. And so actually, all of our models are actually doing pretty similar across all the different hyperparameters. So you've got mtry down here, the number of randomly selected predictors, and the number of trees representing the different colors here. And so actually, what would you do in practice? We want our model to generalize best to an unseen data. So when you actually get accuracy that's looking kind of similar across all your different hyperparameters, the best thing to do is actually just go for the most simple model, because that's the one that's actually going to generalize best. And what's nice about tidy models is they actually have particular functions that don't just select the hyperparameters that gave you the best of a particular metric, but gave you nearish the best, but also are the most simple. And so there's this function here, select by one standard error, which basically looks at all the different scores that you got, and it groups all of the different hyperparameter combinations that were within one standard error of the best one, and then it just looks for the most simple. So as long as it's nearish the best, it will just pick out the most simple. And that's what we get here. If we give our fitted model and run select by one standard error, saying that we are looking for the best with respect to this metric, ROC AUC, it chooses some parameters for us, and it actually chooses the most simple ones we actually went for, which were 500 trees and 5 randomly selected predictors for each of them. Cool, and then we are basically done. We are now ready to just fit onto all of our training data and finally use that holdout test set that we've not touched for this entire time. And again, tidy models with some really nice functions. We can use finalize workflow, and that's going to take our workflow that we had before. And remember, this included a model specification where we just had placeholders for our hyperparameters. So you see we've got mtry as tune here, trees here as tune here, and it's just going to update them with those hyperparameters that we got from select by one standard error. So you just do finalize workflow, give in your best hyperparameters, and it's going to update that as a new workflow using your best hyperparameters. So now that we've decided exactly what algorithm we're going to use, what recipe steps we're going to use, and the best hyperparameters, we're going to finally fit on all of our training data and test on our completely unseen, untouched lyrics test data set. And what's cool about this is you can do that fitting and that testing all in one go in tidy models by using this function last_fit and actually giving your split object. So if I jump back up to right at the top, just to show you where we got that object, this is right at the start. Remember, we did initial split of the full lyrics data set using 70-30 split and stratifying on genre, and that gave us this split object from which we could actually extract the true data sets underneath. But really, this contains all the information. It contains all the data, and it says which are training and which are test sets. So actually, because it knows what's training and what's test, we can just give this whole thing into our function here, last fit, which is what we do here. So we just give it that lyric split object. And we can go and collect the metrics and see how it actually did on our unseen test data set. And you see we're now getting pretty good scores of 75% accuracy. So just looking at the lyrics that we've got in our data set and using those pre-trained word embeddings that we just downloaded off the internet, we are pretty well managing to work out whether or not we've got black metal, death metal, or power metal, which is really cool. And once again, you can do things like just recreating your rock curves. And again, nice to see that it's looking even more towards that top left, which means that our classifier is doing pretty well over all the different thresholds. And then the final thing you might want to do is compare your final model to some of the original models. So we just create a plot here where we collect the predictions from our final fitted model. So these are going to be on our test set. So if you remember, we had 11,000 rows and we got 30% of those in the test set. So our predictions, we're going to have 3,700 predictions, 30% of our full data set. And I'm basically just going to bind those on to predictions we got from previous models and then plot a ROC curve for each of them just to get a nice plot back out so that we can see how our model has improved by changing particular things. So if we zoom in, we can see that the new tuned random forest is this red one, and it's looking pretty much on top, definitely on top for death metal, definitely on top only just for power metal, and pretty much exactly the same for black metal compared to the blue one, which is the untuned random forest. So tuning has helped in some scenarios, less so in black, but definitely so in death metal. And then we also have the rock curve for our untuned naive Bayes model. Remember that original one that we had, which is obviously looking quite terrible in comparison to what we now have. Cool, okay, so that is the end. That's the final model that we fit. Yeah, I think that's everything. Thank you very much for listening. I hope you all enjoyed it. Thank you.